Hello, in this video I'm going to talk about a derivation of the Suvat equations of motion. This is the first video in my series on A-level mechanics, which actually will likely extend beyond level 3. I'm going to do a number of series on physics, this series on A-level mechanics, another separate series on A-level physics, which also will likely extend beyond level 3, and then yet another series in physics, which will be my main series, and certainly the most active series on this channel in the long run, sort of based around my studies at university and my pursuit of a PhD in theoretical physics. So I'm still sort of thinking about the logistics of these series and how I'm going to organize anything, but that's sort of the general plan. And one of the reasons I wanted to do a series on mechanics is that just personally in my leisure time I really enjoy working on mechanics problems. I find them to be a lot of fun, and instead of just jumping into some really cool and big mechanics problems, I thought it would be a good idea for this series to just start basically at the foundations and just work up to that point. And so we're going to start with a derivation of the Suvat equations of motion. Now there are a couple of ways to derive these equations, and you can see them on the right hand side here. And one way, which is my favorite way, is to use calculus. I'm going to save that for a separate video. In this video, we're going to think through what I would describe as possibly a more intuitive derivation. And the reason I say that is because we're just going to build off and derive these equations from a velocity time graph, just a really basic, simple, somewhat arbitrary velocity time graph. And from that we'll be able to think about why these equations work, where they come from, and why they only work when acceleration is constant. And so to start, I'm just beginning to draw a velocity time graph here. And we can write velocity here and velocities in meters per second. So I have that written there, and as you can see at the top I have Suvat here, so S equals displacement in meters, U is the initial velocity, meters per second, and so on. And I'm just going to pick an arbitrary point here and call it U. That's our initial velocity, and I'm going to draw a straight line up like this, again just some arbitrary point in a line, and then at this point here across I'm going to just note that as V, that's our final velocity, and then at this point down I'm going to call that T. That's the time taken to get to our final velocity, V. Okay, and I suppose the main thing to point out at the outset is that this is clearly a straight line. It's linear, it's constant. In calculus or elsewhere one might already be used to seeing crazy curves and working with crazy curves that are all over the place. But this is a straight line. It's constant, and the gradient of this line, the gradient equals acceleration, and thus one may already get a sense of why these equations work best, really, when it comes to studying objects that are moving only with constant acceleration, or I suppose to phrase it differently, why they are used to derive equations for objects moving with constant acceleration. And so if the gradient equals the acceleration, we can think more about this in that we can sort of rewrite this as delta V over delta T, which is the change, and I suppose this is one of the stated assumptions behind this derivation, is that the acceleration equals change in speed over time. And so what is change in speed? What is delta V? Well, delta V is just going to be V minus U, and we can put that over T, and of course that's going to equal acceleration A. Alright, and now from this point we can sort of just build on this logic and expand on it and find our first equation of motion. and what we want to do is make v the subject. And so I'm just going to rewrite that down here. We have v minus u over t equals a, and so we're just going to multiply by t on both sides of this equation, and that, of course, the purpose of that is to cancel out the denominator here on the left hand side, and so we end up with v minus u equals a t, and we just want to add u to both sides, just simple algebra, and we get v equals u plus a t. Okay, so velocity equals initial velocity plus acceleration times time, or final velocity, I should say. Yeah. So, and I'll just denote that as 1. That is our first equation of motion. Now, to arrive at the second equation of motion, we have to continue with a bit of logic. And I suppose it's important to point out and to understand that the area under this line, which I'll highlight in purple, the area here equals displacement. And I'll write it this way: area equals displacement. It's a bit messy, but sure it's legible enough. So area equals displacement. And I guess it's worth noting that in fact the area under any velocity time graph is equal to displacement, even if the velocity is changing. And this is, I suppose, why velocity time graphs are especially useful, because their gradient equals acceleration and their area equals displacement. And to find the area, really we just want to look at the average velocity over the time taken to get to that point. And we can write this as, and maybe I'll just write area equals s, right, displacement s, and we just, so, and then we can write the total displacement. It equals the average velocity, which is u plus v over 2 times the time taken, so times t. And that is our second equation of motion. Now, to arrive at the third, fourth, and fifth equations of motion, really we just need to use some algebra, just a bit of algebraic manipulation, really, and it's fairly straightforward from this point, in fact, because to arrive at the third equation of motion, all we're going to need to do here is substitute equation 1 into equation 2. So it's just a little bit of algebra. So I'll write it here on the left hand side. We know v equals, for equation 1, u plus at. We know the total displacement s equals u plus v over 2 times t. We're going to substitute 1 into 2, so we can write s equals, well, we have s equals u plus v, well, v here equals u plus at, so we can write plus u plus at, and of course all of that still over 2 times t. And now we can actually rewrite this. We can pull 1/2 out of front, times u plus at times t, just to make things a bit more explicit, and we can simplify what's in the parentheses here, which is u plus u is 2u plus at, so we can write 2u plus at. And now we just use the distributive property. We multiply by 1/2 right across, and likewise we multiply by t right across, and what happens is that this 2 cancels, so we end up getting s equals, and it's being multiplied by t of course as well, so we end up s equals ut plus 1/2 at squared. And that is our third equation of motion. Now we'll denote that with a 3. And to arrive at the fourth equation of motion, we're essentially just going to take the same steps, except we want to substitute for u instead of v. And so what that requires is that we just rewrite the first equation a little bit by making in order to make u the subject. So I'll just write that here. So we have v equals u plus at, right, as we see here. And now we just want to subtract at from both sides. So you get v minus at equals u. Or maybe I'll write it this way: u equals v minus at. And so we're just going to substitute this again into the second equation. And I'll just write that in this space here where we have total displacement S equals U plus V over 2. Well, U now is V minus AT. We want to substitute that in. So V minus AT plus V over 2 times T. And what we can do actually, just to make all the steps explicit, I'm just going to pull the 1/2 out front. We have V minus AT plus V times T. And so we have V minus AT plus V in the parentheses. Well, we have V plus V, right? We have two V's, so we can simplify this as 2V minus AT. And again, we're just going to use the distributive property right across, and the 2 cancels here. And so what we end up with is S equals VT minus 1/2 AT squared. And that is the third equation of motion. As we can see up on the list, if we scroll up, you can see S equals VT minus 1/2 AT squared. Now there's actually another way to think about, and I'll just note that that's the fourth equation of motion, I should say. So there's another way to think about the third and fourth equations of motion, actually directly in relation to velocity time graphs, and I might do a separate video on that as just a little bit of an extension of this video. It offers more of a visual representation as to why, where these equations come from, and sort of in relation to, explicitly, directly in relation to a velocity time graphs, similar to what has been highlighted in working out the first two. And so I'll save that for a separate video in order to save time and keep this video short. Because really now all we need to do is to derive the fifth equation. And I suppose what's interesting to highlight at this point before moving forward is that all the equations that we've derived so far have T, don't they? All of the equations that we've derived so far include T. And so what we want to do to derive the final fifth equation is basically to get an expression for T, and then we can just substitute it into any one of these equations here. And so what's common, what people will commonly do, and I'll do the same thing here, is I'm going to make T the subject of the first equation. I'm just going to rewrite the first equation. So if I scroll down to give myself a bit of space, but enough to see all four of them. Okay, so we have, in the first equation, we know that V equals U plus A T. We want T to be the subject. And so what we can do is we can subtract, well, first we can start by subtracting U from both sides. So we get V minus U equals A T. And now we can just divide by A on both sides here. And so that leaves us with T equals V minus U over A. Did I do that right? V minus U over A. Yeah, okay, yeah. And what we want to do, yeah, I've done that right, I think. What we want to do now is take this expression for T, where T is the subject, and substitute it into any one of these equations. I'll just substitute it into equation 2. And so if I maybe highlight, if I do this, I'll just draw an arrow here and just give myself some more space. We have equation 2, which is S equals U plus V over 2. I'll just wrap that parentheses, okay, and times T. Well, T equals V minus U over A. So times V minus U over A. Now, how do we simplify this? Well, we can multiply by 2 on both sides to cancel the denominator here, and we can multiply by A. And that will simplify things nicely, actually. And so to actually highlight that, I'll write it this way, keeping everything very explicit. We have multiplying by 2 on both sides and by A on both sides, by 2 and by A. So that cancels the denominator here and here. That's the whole point. And so what we end up with here is 2AS equals U plus v times v minus u. And we can essentially just FOIL this out, or use the distributive property twice, however you want to think about it, or it's like u times v, u times negative u, and v times v, and v times negative u. So that leaves us with 2as. Well, u times v, it's just uv. U times negative u is negative u squared. V times v is plus v squared, and we have v times negative u, so minus uv. And notice that we have uv, a positive uv and a negative uv, and quite conveniently they cancel out for us. These cancel. And so if I just scroll down for one moment here, and so what we end up with is 2as equals v squared minus u squared. We're not quite done, because as you can see here, the fifth equation, it's v squared equals u squared plus 2as, and so we need v squared to be the subject. How do we do that? Well, it's simple, right? We just add u squared to both sides, and that gives us v squared equals u squared plus 2as. That is our fifth equation of motion. And I suppose it's to conclude, it's an interesting point, maybe, I don't know, a contextual point, that the reason that there are 5 equations of motion is because there are 5 variables, and that goes right back up to the top here, where we have s for Suvat, right? 5 variables: s equals displacement, u initial velocity, v final velocity, acceleration a, and t for time. It's 5 variables, and that's the reason that we have 5 equations, because essentially this means that because there are 5 variables, each equation essentially eliminates one of those variables. So if we know the values of any 3 of the variables, we can calculate the other 2. And so, yeah, but that concludes this video.